Welcome to my talk on the synergy of graph data management and graph machine learning. I'm Arijit Khan and I'm an associate professor at Aalborg University in Denmark. Let me get the pointer. So before I start, some background about myself. I did my PhD from UC Santa Barbara, and during that period, I also did a couple of internships at IBM TJ Watson and Yahoo Labs in Barcelona. Then I moved to the systems group at ETH Zurich as a postdoc for a couple of years. I had been an assistant professor at Nanyang Technological University, which is NTU in Singapore. And for the last couple of years, I am in Aalborg University as an associate professor in their computer science department. So let's start. Okay, so I work on graphs, in particular graph data, and they can be found almost everywhere. For example, in one setting, we can see a lot of small scale graphs that can be stored in a graph database, such as chemical compound structure. Now, in chemical compound, you have those atoms that can be represented as the nodes of a graph, and then there are bonds across those atoms, so that can be modeled as edges. And each chemical compound is relatively small, so you have some small scale graphs, but there are many of that, so you can load them in a graph database. Similarly, human brain can also be modeled as a graph because you can do the fMRI scan of the human brain, and then you can find different important locations. And these are the nodes of the graph. And then based on their connectivity, you can form edges. So we have a graph data out of human brain. And in a hospital setting, there are many such patients. From each such patient, you can get a graph structure and we can load them in graph database. But then on the other setting, we also see a very large graph, like millions or even billions of nodes and edges. There's only one of that, such as social network, road network. You can think of these days all the knowledge bases, such as knowledge graphs, DBpedia, Freebase, etc. So they have only one graph, but it's very large scale. And this is a different setting than having only like one graph database with many graphs. And then these graphs also come in many different varieties. So on one hand, we see static graph that doesn't change a lot. For example, chemical compound structure. But then on the other hand, we also see dynamic or time evolving graphs. Think of road networks where the distance, right, can change over time, or the travel time can change due to different traffic conditions. And we can store the historic or the snapshot data over time, and we can get different snapshots of road networks which are different from each other over time. And then if we think of the communication data, such as social media, IP traffic, etc., then the graph structure changes very rapidly, right? So the graph edges are coming as the graph stream. And from static network, we have very dynamic or stream kind of graph structure data. Then we can also have varieties in the context of the nodes, edges, their types, and the additional information that they can store. For example, we think of, let's say, the sensor network or the communication network where the link between two nodes can fail with certain probability. So we can associate some probability value that what is the chance that this edge will exist between two nodes, and we get an uncertain graph. Similarly, we can also associate different properties with the nodes, such as DBLP, right? In DBLP, we have information about different publications. So we have nodes as authors, nodes as papers, nodes as conference venues, right? Journals, etc. So it's a very heterogeneous kind of graph where you have nodes of many different types and also connection of many different types. And these days, knowledge graph is quite popular, and they basically model different kind of relationships across various entities. For example, who established a company, who acted in this movie, or who won this award, etc. These are also very heterogeneous in nature in terms of both the types of nodes and the edges. Last but not least, these days we also see a lot of research work on higher order graphs, where we not only care about two nodes being connected by an edge, but oftentimes it's an interaction involving multiple parties, more than two nodes. So again, think of this DBLP network where we see publications, and each publication consists of not just two authors, but in many cases, multiple authors. So that means it's an interaction involving multiple parties, and you can model it as a hyperedge connecting multiple nodes. Similarly, in case of a social event, there are many participants, and you can also model an event as a hyperage with many such nodes. So we get a higher order structure such as hypergraph. So clearly, we see a lot of varieties in the form of graph data, and that's why when we look at the applications, there are also many different varieties. And to solve some of those problems, there is no unique solution, right? No unique machine learning or database systems that I can build that can solve all of these graph problems, right? So no one size fits all. And these days, machine learning is very popular, and in particular, the deep neural network. So similarly, in the context of graphs, we are also working on graph neural networks. So what it does is it performs different kind of downstream tasks such as graph classification, node classification, link prediction, etc. over the graph data. But in general, machine learning is very difficult to be performed on graphs because of the irregular structure of the graph data, right? It's not like images. So here a node can get connected to any other node in any part of the graph. And that's why you first need to convert them in some kind of regular structure, such as vector representation. And this is also called embedding or representation learning, where we create some regular vector structure out of the nodes, out of the edges or the graph itself. And then we apply some machine learning technique like a GNN model to train on top of those vectors and do different downstream tasks. But of course, the benefit of deep neural networks such as GNN is that these embeddings are generated implicitly, right? It's not generated explicitly. So that means the training can be done in an end-to-end manner based on the quality of the downstream task that we want to perform. Now, there are also many varieties of graph neural networks. One of the most popular one is called graph convolutional neural network, or GCN. On a very high level, I will discuss what it does because we will use some of these techniques later on to discuss more specific works that we have done in this setting. So the basic idea of graph convolutional neural network is that every node starts with its own feature vector, which are a set of feature values, right? And then they propagate this feature information to their neighbors, and they aggregate it based on whatever they are getting from their neighbors. And then if you keep doing it for multiple rounds, that means each node then will get information from multiple neighbors across multiple hops. And that you aggregate and create a new vector representation at each node. And that's the node embedding that you generate, right? Once the embedding is generated, then we apply different kind of machine learning techniques to perform downstream tasks, such as node classification, graph classification, link prediction, etc. So what are these tasks in real context? Well, if you think of node classification, then let's assume a financial transaction network such as blockchain, right? And in the blockchain setting, we can ask whether an account is malicious or not, right? So that's basically node classification problem. Or in the context of graph classification, given a chemical compound, we can also classify into multiple classes. For example, whether this chemical compound or medicine can cause cancer as side effect or not. So that's where we are classifying the entire chemical compound, and we can get a graph classification problem. Then link prediction is about predicting an age between two nodes. And we often see examples in social networks, right? So we often get recommendation that you should connect to another user, which probably you don't know, but maybe he or she is your friends of friends, right? And similarly, you can also think of item recommendation in movie network or co-purchase network, etc. Now, based on these three basic tasks at the level of nodes, graphs, or edges, we can also combine them and we can solve more complex tasks using this kind of graph neural network techniques. And these complex tasks could be entity resolution, question answering, or even drug design. So clearly, these are very interesting and challenging problems these days. And machine learning, in particular graph machine learning, can be very useful to solve some of these interesting problems. Now, I come mostly from the data management background, right? That means I deal with how to clean the data, how to model the data, how to uh, how to store it, how to query it, etc. And what we are looking into is how this kind of data management aspect can be combined with data with the machine learning aspect and how they benefit each other. Okay. So if you think of the machine learning task over graph data, then the graph data actually go through a number of steps before the actual machine learning model can be applied on them. So the first step is, of course, creating the graph out of raw data, which could be text, table, etc. Then you need to clean it, you need to augment it, right? Maybe there are some noise, mislabels, etc. The next step is creating the vector representation, which is the node embedding, right, that I have shown in the previous slides. Once the embeddings are generated, now you need to train your model, such as training of the graph neural network. Once the model is trained, now you perform different downstream tasks on a new test instance, such as a new test node or a new test graph. And finally, at the last step of this pipeline, you also have user in the loop, because ultimately you are solving these problems for domain experts, right? So these neural networks are generally black box in nature. And even though they perform well, we are often not happy because we don't know what is really going on inside, right? Why you are getting such good results. So we need to involve human in the loop. And in particular, we need to explain the decision process of the machine learning models. So that's why we also have explainability at the end of this pipeline. And what we are looking into is how graph data management and graph machine learning can actually integrate and benefit each other at each stage of this pipeline. So here I have shown some examples of our recent works. For example, if we look at graph embedding stage, right? And before I have shown you also examples of very large scale graphs with probably millions or billions of edges. Now, embedding learning or even training of graph neural network is a very expensive process. And if your scale is very large, right? If you have a million scale graph, that's like very, very slow. So how we can apply different data management algorithms such as sampling techniques, random walk-based techniques, etc., and also distributed systems to scale up this kind of embedding learning techniques. So we had a paper in last year's BLDB where we proposed distributed graph embedding to scale up this kind of machine learning techniques. And then one-time embedding might not be sufficient, right? Because the graphs are changed dynamically. And then for small changes, if you need to train again, that's very expensive. So we also need to do incremental processing. And we had a paper 2 years back where we discussed how to perform dynamic or incremental updates in the embedding process. And recently, we also moved into the domain of explainable AI, which is this explainability aspect at the end of the pipeline. And we are looking into problems such as how to explain the decision-making process of graph neural network, how to make it much more usable, how to make it much more robust using different kind of data management techniques. So I will talk more about this GNN explainability part in the first part of my talk. And the focus there will be how to apply different data management techniques to make graph neural network explainability much more useful to the domain experts or the end users. And that's where you will see that how data management can help in graph machine learning. And then on the other direction, how machine learning can help in graph data management. Well, for the data management people, query processing is very important, right? We often write queries in SQL, SparkQL, etc., to query different types of data, such as relational data, graph data. Now, machine learning can help because many times these data are noisy. They often do not have any standard schema. So writing a schema-centric query language might often be very difficult. And we need to take help of machine learning to do different kind of approximate query answer, understanding users' query intent, etc. Right? So these days, researchers are working on natural language to structured query language, such as NLP to SQL, NLP to SparkQL, etc. So that's where machine learning can also benefit, right? And these are the two directions that we are looking into. First part of the talk will be focusing on how data management can help in graph machine learning, looking into the explainability aspect. And in the second part, I will talk about how machine learning can help in query answering or in particular data management. Okay, but before I start, this is also another like way of discussing some of the or categorizing the work that we do. So we work on different aspects of graph data management, such as graph querying or knowledge graph querying, then querying uncertain graphs, because as I have said, oftentimes you have uncertainty with the edges because of the communication failure. So we also need to do processing of uncertain graphs, such as reachability, shortest path, etc., community detection, etc., over those uncertain graphs. Then we also work on complex graph mining, such as finding important correlations across diseases or genes, etc., right, in a biological network that can reveal important hidden interactions that probably you don't see if you look at it on a very like simple setting. And then to support this kind of complex querying and analytics, we also design large-scale in-memory distributed systems. So the work that I mentioned in last year's VLDB, there we applied distributed systems technique to scale up the training of graph neural network. And more recently, we are also working on the explainability aspect, which I will focus next in my talk. Okay, so let's start with explainability. But before I go into more of the details of some of our works, I would like to mention that feel free to ask questions. So if you have any questions, interrupt me anytime. And then this talk will also not be very technical, right? Simply because of the limitation of the time. The key focus here will be, I will give the kind of problems that we are solving, why they are important, and then I will give very high level intuition of how we are solving them, right? What kind of algorithms or systems we are designing without going into too much details. And then similarly, when I will discuss some of the experimental results, I will give very high level overview of some of our key results without going into too much details. But if you have questions, please feel free to follow up later. Okay, so about explainability of graph neural network, it simply means these graph neural networks are black box, right? They are end to end. So we want to explain their good results to domain experts. And this can be done at the level of individual instances. For example, I have a test node and I classify it. Now I want to understand why it is classified as malicious. Or it could be at the model level, right? So I want to understand the behavior of the model and generally in the context of a positive class or a negative class, right? Like what are the key patterns for this positive class? And why this is important? Well, because ultimately we are providing results for the end users, and these end users could be biologists, social scientists, policymakers. So it's very important that they understand the decision-making process, right, at some level. And then in many safety critical applications such as autonomous driving in health and Medicare, it's also important that we want to deploy this model. And before deploying, some trust needs to be built with the domain experts. So we also want to explain these models. And last but not least, in many countries such as Europe, there are also legal requirements such as GDPR. So you not only need to provide good decisions from your algorithm, but you also need to explain why your algorithm provides such results. So considering all these aspects, explainability of deep neural networks such as GNN is a very important problem. Now, what are the challenges? Well, the key challenge is there is no unique definition of explainability. Okay, it's mostly the human aspect, right? We are trying to explain things for end users who are human beings, and there could be many different requirements. For example, I want to trust the model. I want to understand things at a very low level, mechanistic level in terms of the model's parameters, layers, architecture, etc. Or maybe I want to understand things at a more user-friendly manner. I do not want to care about too much about the mechanical details, right? And that's why there is no unique definition. And also given two explanations comparing them or evaluating them, right? Which one is better? It's very difficult, right? So there is no unique way. Of course, there are different metrics, but oftentimes there is also no ground truth for those real world data. So that makes the problem very much challenging. And in summary, the challenge is the subjective aspect, right? So it's a subjective problem. We are trying to help the domain experts, and there are a lot of subjective notions involved here, right? What is a good explanation? And then generating a good explanation for some end users is that's why very, very challenging. So what we are looking into, well, we are looking into the usability aspects, meaning how to make those explanations much more user friendly or usable to domain experts, how they can understand them well, how they can match their domain knowledge against these explanations, and how to make those explanations much more fair, robust, etc. And we will see that how different data management techniques can be useful here to make the explanations more usable, robust, and fair. Okay. So in this context, I will talk about our recent works. So the first one is to make the explanations more usable, and we had a paper in this year's SIGMOD. Then we also had a paper in ICD, which is about making explanations more robust and robust against minor changes in the graph data. Because if there are minor or insignificant changes in the data, you don't want the decision of the model and the decision of the explainability method change drastically, right? If that happens, then of course it means you can't build trust on your model. And then I will also talk about a bit of counterfactual evidence to get fairness out of this kind of explainability results. And again, fairness, bias, etc., are very critical these days, right, in the context of both data management and machine learning. Okay, so let's start with our one on the explainability part, or to make explainability more usable to the domain experts. And to motivate this, let's look at this example. Okay. So we see that there are two classes of chemical compounds on the bottom. We have mutagen class and non-mutagen class. And this simply means that the mutagen class, these compounds, they mutate very easily to another compound. Whereas non-mutagen class, it means those compounds, they are very difficult to mutate to another one. So we have two categories of chemical compounds, and then you can train a GNN model on top of them, and given a new compound, using this pre-trained model, you can predict what is its class, right? Whether it will be mutagenetic or not. But domain experts like chemists may not be happy. They also want to understand, right, which substructure of this chemical compound is really the key reason behind such decision making. So the next step, what you can do is to apply different existing explainability methods for graph neural networks. If you apply them, then these are some of the explanation subgraphs that we get corresponding to two different classes. So for the mutagen class, we get such explanations like these two, one GS1 and GS2. And then for non-mutagens, we get GS3 and GS4. This is what existing explainability method can already provide. But what are the problems here? Well, if you look at these explanations, they are still relatively large, right? They are not as large as the original, the mutagen, original chemical compound, but they're still large. And domain experts still don't understand, make any sense out of them. Yes. Yeah, it's like some substructure that are highly correlated with respect to the decision of the model. Okay, so these substructures are highly correlated with respect to the positive class, and these substructures are highly correlated with respect to the negative class. That's how most of the existing explainability methods work. Okay, on a very high level. But they're not very useful because they are still relatively large, and domain experts often have very specific knowledge, right? For example, they know terms like benzene ring, some toxicophore like NH2, NO2, etc. Like this is a typical knowledge that NO2 is a toxicophore, and if it is present in a compound, then most likely it will be mutagenetic. But looking at this kind of large explanations, it's very hard for them to further analyze and query them and then figure out. For example, if I give this explanation, it's hard for them to answer queries like which toxicophore occurs only in mutagen or which toxicophore occurs in both mutagen and non-mutagen. So what we provide is a more summarized view on top of those explanations, and that you see as patterns on the top level. So what we do is some kind of constant graph pattern mining to extract even smaller patterns that the domain expert can identify easily. For example, these benzene rings, right? We can see that they appear in both mutagen and non-mutagen. And this is a very important information because it says that although the presence of benzene ring is important for this classification, but it's not very discriminative, right? It appears in both classes. Whereas this pattern NHNO2, yeah, this is let me see. Yeah, NO2. This is like a signature of mutagen, right? So this is also what we can detect. So this is very discriminative, right? It doesn't happen in non-mutagen, but it happens only in mutagen. So when we provide this kind of explanations at a very precise or fine-grained level, then domain experts can easily understand and match against their domain knowledge. So that's the goal that we try to solve. So, so these are some of the challenges with the existing approaches. Their explanations are large, and often they have a lot of repetition or some of the stuffs that are not so useful or meaningless to the domain experts, right? And last but not least, they are also not configurable or tunable. What do we mean by that? Well, if you think in the context of, let's say, images, right? So we can give the features of different animals. Let's say I have images of different classes of animals like dogs, cats, and snakes, right? So the existing explainability method, they can explain individual instance, or they can also explain classes, like what are the typical features for dogs versus cats, etc. But what if I'm interested across multiple classes, right? Like what are the common features of both dogs and cats? And then how can I distinguish them from the features of some other animal like snakes, right? So this kind of tunability where I'm interested across multiple classes is not possible in the existing explainability methods. But that's also what we want to provide. How? So here we have an example, of course, from the graph domain, because that's what we are working on. And here we work with, we look into the example of the Reddit social network. And in Reddit social network, we find two types of major communities. One is online discussion, another is question answer. Now, we find that their structure in the form of graph are quite different. So for online discussion, usually what happens is one person posts something, then because it's a discussion, followed by another person, followed by another person, and so on. So oftentimes you see a chain kind of structure, a linear structure like a chain or a tree. On the other hand, for question answering, what we find out that there are two groups of users, some common or naive users who are just posing their questions, and then there are some experts who are answering those questions as many as possible. So oftentimes you see a click or more dense structure such as a bipartite click, right? So we see that if you are interested in the individual classes such as online discussion, we will find the more linear structure, and if you're interested only in the question answering, then we find more click or by click kind of structure. But what about something in the middle? For example, what if I'm interested in the common feature of both, right? So in our model, we can actually give equal importance on both classes, and then we can find something in the middle as well, right? So we see something that is neither completely click and neither completely linear. And that is what I mean by configurability. So our method can also support this kind of tunability where users can specify their levels of interest over multiple classes. And to support that, now we do two tiers of explanation. At the lower tier, we provide good quality explanation subgraph, which are still relatively large, but they are highly correlated with respect to the decision of the model. And then on top of that, we apply different kinds of graph pattern mining techniques to identify smaller patterns that can summarize those lower tier explanation subgraphs. So we have these two tiers, the lower tier, bigger explanation subgraphs, and then higher tier that can summarize those explanation subgraphs in the form of smaller patterns that the domain expert can easily identify based on their domain knowledge. Now, we formulate this in a technical problem. We call it graph view because we expect our higher tier patterns to cover the lower tier explanation subgraphs, right, in the form of, or in terms of the nodes. So because we have this node coverage aspect, that's why it's similar to the notion of graph view from the domain of graph data management. So our goal is to get these graph views that automatically consist of two tiers, the higher tier patterns and the lower tier expansion subgraphs. And we expect them to cover well, okay? Now, for these expression subgraphs, we also have them high correlation with respect to the decision of the model, and that can be expressed using this kind of factual and counterfactual notion. So what do we mean by that? Well, factuality means if you only look at the explanation, you should still get the same result as in the original graph, right? So that's like showing a very high correlation with respect to the presence of the explanation. So if you only apply GS to the model, which is the explanation, then you get the same decision as in the original graph G, right? Your decision does not change. Now, the other direction is the counterfactuality, meaning if you change something within the explanation, then you should not get the same decision. So that is what counterfactuality measures, and that's what we write here. If you change something in the explanation, then your decision should be different. And that basically shows that your explanation is highly correlated with respect to the decision of the model. Okay, now satisfying these two properties, right? We want to get this kind of graph views consisting of both the lower tier explanation subgraphs and the higher tier patterns, but we find out that still there could be many possible solutions. So we want something, a unique solution that is also of good quality. Now, how do we measure the quality? Well, we have two terms that we incorporated in our objective function, and they are based on the feature influence, and I will explain them, and the other is diversity. What do you mean by that? Well, if you remember this notion of message propagation in the graph convolutional neural network, where each node propagates its features to its neighbors, neighbors of neighbors, and so on. So this kind of message propagation can also be modeled as a type of random walk, right? So you are propagating your information to your neighbors, neighbors of neighbors, etc. And through that process, you are also incurring some influence on your neighbors, neighbors of neighbors, etc. So we want to capture those nodes that have very high influence on their neighbors because they are really important in the context of message passing. And that's exactly the feature influence captures. So we want in our solution those nodes that have high feature influence. But at the same time, we do not want to incorporate two nodes that have the same influence region, right? So this is also similar to set cover kind of problem. You want to cover all the elements with limited number of sets, but at the same time, you do not want to include two sets in your solution that cover the same set of elements, right? So in the same way, we want high feature influence in my solution, but at the same time, I also want some diversity so that when I aggregate those nodes that are part of my solution, I can get overall very high influence, right, on the rest of the nodes that are not part of my solution. So this is how we formulate our problem, right? We want to generate graph views at two layers. And then on the explanation subgraph level, we also want to satisfy certain kind of cardinality constraints from multiple classes that we have, so that we can apply some configurability. And finally, among those that satisfy this criteria, we want to get the one that maximizes this explainability, which combines both inference core plus diversity. So before going into the actual solution, I would like to discuss what is the computational complexity, or how challenging is it to solve this problem. I'll not go into the technical details, but we have the theoretical analysis, and we have shown that the verification problem is NP hard, simply because you need to verify some kind of subgraph isomorphism aspect, and then the generation problem is much harder. However, the good thing is, if you think of our objective function, which is to maximize the inference core while also applying some kind of diversity, that is monotone submodular. And this is very similar to the notion of set cover, right? So in set cover also, the objective function is monotone submodular. So that means you can apply similar notions of greedy inclusion in an iterative way, right? Such that you can still get a good solution with an approximation guarantee. So what we do is basically we select the node that have the high influence each time, and then next time when I'm selecting the next best node, then I select the node among the remaining ones, right? The remaining nodes that are not covered by the previously selected. So it's very similar notion as how you solve set cover problem, okay? And that's why we can also apply some of their approximation guarantee. So here these guarantees are coming mostly from the literature. So we have shown that if our graph database is static, then we get half approximation with our greedy approach. And if the graph database is coming more as a streaming fashion, that means you are keep adding graphs dynamically, then you get 1/4 approximation. And we also did parallelization of both the algorithms. I'll not go into the technical details due to the limitation of time, but just to give you the flavor how we solve this problem. We also had a demonstration paper in Sigmod, and here we build our system. So it consists of 3 layers. On the bottom layer, we have the graph databases coming from different domains such as chemistry, biology, social networks, etc. And then in the middle tier, we have our algorithm modules. So it starts with finding the important nodes, and then we group them and we verify if the group satisfies both factuality and counterfactuality, then it's a promising solution. And once we get the subgraphs at the lower tier, then we apply different subgraph mining techniques to identify the higher tier patterns. Okay, so that's how our algorithm on a whole works. And then we have the interface layer at the outside, where user can visualize these explanation subgraphs at 2 tiers, and they can also interact with them. For example, they can tune the parameter of how much importance they want to provide across different classes, and based on that, they can get different kind of explanations. So I will discuss some experimental results next. So we have some metrics to measure the quality of our method, and these metrics like fidelity plus and fidelity minus are quite standard to measure the factual and counterfactual aspects of the explanation that we generate. So what fidelity plus measures is if you change your explanation, then how much the decision of the model changes. And if it changes a lot, that's a good thing. That basically means that that the explanation was indeed useful, right? Indeed very relevant. Because you change the explanation, now your decision changes. So so that means high fidelity plus is a good thing, right? And that's exactly what we get compared to some of the other baselines. So both our method AG, which is on the static version, and SG, which is on the streaming version, they have high fidelity plus compared to some of the existing methods that we compare. Then on the fidelity minus, what we do is we actually keep the explanation fixed, and we change outside the explanation. And because explanation is the key reason behind the decision of the model, that means any change you do outside should not impact the decision of the model. So that's why a lower value of fidelity minus is better, and that's also what we get compared to some of the existing explainability methods. So these metrics shows that the explanation subgraph that we generate are of quite high quality. Then in terms of the sparsity, it measures how concise your explanation is, because you not only want explanation of very high quality, but you also want them to be small or relatively small, so that users can inspect them well and they can try to match their domain knowledge. And higher sparsity is better, because higher sparsity means the explanation is of small size. And that's also what we get often compared to some of the existing methods. So our sparsity is generally higher, and that basically means we not only get high quality explanation, but also of smaller sizes. Okay. And finally, I will discuss some of the runtime results. So here, in terms of the runtime, because we compare against existing explainability methods that are published mostly in the machine learning venues. As you see here, our baselines are mostly taken from the machine learning domain. They often do not care about runtime. They do not show any runtime results, right? They only report the quality results like fidelity plus, fidelity minus, etc. But we also care about runtime, because if your explanation generation takes hours or even days, then that's not a good thing. And not only that, we also show parallelization. So first of all, we show that our explanation generation is quite fast, and then it can further be improved by using more number of servers or threads. So this also shows the efficiency aspect of our algorithms. Okay, so that concludes the first work, which is how to make the explanations much more usable. And then in the remaining part, I will, on a very high level, I will introduce the two other problems that we are working in this phase, which is how to make the explanations much more robust. Okay. So what do we mean by robust? Well, we first of all, we still want to maintain those two aspects, which is factual and counterfactual. Meaning, if you consider only the explanation, your decision should be the same by the model. And if you remove or perturb the explanation, then your decision should change, right? That indicates very high correlation with respect to the explanation and the decision of the model. But then we also add a new constraint or new criteria here. We call it K robustness. And it means that outside the explanation, if we remove up to k edges, then we can still ensure that the model will produce the same result, and the explanation model will also produce the same explanation. Because if those k edges are outside the explanation, which is key part of the graph that is producing the decision, then that are kind of insignificant, right? So by changing them, your decision and the explainability that you get should not change drastically, right? So that's why we also want to incorporate this robustness criteria. And here we also have a case study from a real cybersecurity domain. So I'll explain what we have demonstrated as our case study as an application of this problem. So assume that we have a flow of how the control goes from one process to another. So this email, right? This email actually embeds a malware, and the goal of the malware is to get access to the bridge.sh file, because through that access, it can also get access to many other data that are in the server. But any path to bridge.sh is not give it access to the rest of the data. It must also get access to the privileged files such as sshIDRSA to cmd to bridge.sh, or sshIDRSA to cmd to sudoers to bridge.sh. So these two red paths that you see from root to bridge.sh are the valid attack paths. That means if the attack happens to these red paths, then only you get the required access, and then through that access of bridge.sh, you can get rest of the access in the server. But there are also some deceptive paths that goes to these green nodes, like the files, etc., like from malware to ddos.exe to home to bridge.sh. So this is a deceptive path. If the attack happens to that path, then it will not get the privileged access, and it will not be able to attack rest of the files. Now, what the bad guys or the malware guys will do, they will actually create a lot of false attacks, lot of deceptive attacks, so that the security expert, if this is not a very like expert guy, then he will put the security resources on those deceptive paths, and soon the resources will be exhausted, and then the actual attack will happen through those red paths, and then you will get the required access, right? So what we want is that we not only want to classify bridge.sh as vulnerable, but we also want to provide some kind of justification, right? Some explanation that why this is vulnerable. And we want to identify these red paths in our inclusion, in our explanation, right? And if we can incorporate that, then that actually help us to decide where the security resources should be incorporated. And our K robustness problem can actually solve this, because if you change a little bit on the path that goes to the green files, then nothing will change in terms of the decision on bridge.sh. But if you change on this path, which are consist of the red attack paths, then bridge.sh decision will be different. So that's why our K robustness problem can also detect this kind of important subgraphs, right, that consist of the real attack paths. And that shows the usefulness in the cybersecurity domain. Okay, so given these interesting applications, now we formulate the problem. We have three aspects: factual, explanation, meaning if I only consider the explanation, the decision remains the same. Counterfactual explanation, meaning if I change something on the explanation, the decision changes. But we also have K robustness, meaning outside the explanation, if I change up to K edges, nothing will change in terms of the previous two aspects, right? So before solving the problem, we analyze its complexity and we find that this verification problem is NP-hard simply because when you look for all those K subset of edges outside the explanation, you have many possibilities, right? So the graph consists of, let's say, m edges, and you have m choose K number of combinations that you need to try, and then see for each of them if your decision changes, right? So that's why it is NP-hard. But of course, we have a more theoretical proof, right, in the paper, how we show that this is NP-hard. And the generation problem is the complementary to this. So this is co-NP-hard. This basically shows that the problem is challenging. So how do we solve it? Well, we don't solve the actual problem, but we add some new constants, which is this local budget B. So remember that initially we only have the budget on the total number of edges that we can change, which is K, but we add a new constant B, which is the amount of change I can make surrounding each node, right? So if we combine this local plus global constant, then we show that the problem becomes polynomial, and then we have a nice solution, an efficient solution to solve it, okay? So we did comparison with the existing literature. Of course, they are either doing only factual or only counterfactual or both, but the robustness is something that we added. So here we have a new metric that we measure, which is the graph edit distance based similarity with respect to the previous explanation. And if we allow certain changes on k edges that you see on the x-axis, then how much the explanation changes, right? If your explanation doesn't change a lot, then that's a good thing, and that's exactly what we get. Our method has very small changes compared to some of the existing methods. So this also shows that we are quite robust. Okay, and then I will introduce the last piece of work before I will try to conclude. So the last piece of work is where we look into the counterfactual evidence aspect of the explainability. And what do we mean by counterfactual evidence? Well, think of let's say getting loans in the in the bank setting, and then we want to see if two users, they are very similar in terms of their features, in terms of their neighborhood structure, etc. But somehow the decision of a pretend model is different on those two users, right? So here we see a man in the middle, and this user actually get loan in the actual test data, whereas this female on the middle, she does not get loan. But when we investigate their feature, their neighborhood structure, we find that they are quite similar. So that means this female example here is the counterfactual evidence of this test user, right? And our goal here is to find out this kind of counterfactual evidence. So given a test node, we want to find the top K counterfactual evidence. How do we solve this problem? Well, the basic idea here is to compare the subgraphs surrounding this node, right? So the subgraphs must be very similar, but the decision of the model will be different, right? Now, how do we compare subgraphs? Well, we convert the subgraphs in the form of vector using the existing kind of embedding techniques, and now we compare two vectors. So this problem now becomes nearest neighbor search over the vector space, right? So vector databases these days are very popular, right? Given a vector, you want to find out other similar vectors. So we can take help of those techniques or different indexing techniques that are there in the vector databases to actually solve our problem, right? So here we show an example of how we started with our problem, then we solve it to the nearest neighbor search over the vector database problems, okay? And then we demonstrate different applications such as revealing unfairness, right? For example, this can clearly show, right? You can find out your counterfactual evidence, and if there is a lot of similarity, but only the sensitive features are different, then that can reveal unfairness in the decision making process of the model. Okay, so that's basically concludes the explainability part. And what I want to give as the take home message is that we are applying different kind of data management techniques such as graph views, usability, robustness, parallelization, fairness, even vector database search to make the explanations much more user friendly to the domain experts. And in terms of the future work, we are also looking into problems such as Pareto optimality, because as I said, there is no unique metric that is good for all explanations, right? It comes from many different requirements. So that means you might look for multi-criteria optimization and an explanation that is good across multiple factors, right? So we are taking help of skylines to solve that problem. Then we are also looking into problems like how to use those explanations for model debugging, right? So if the model gives you wrong decision, then not only want to explain the decision at the very end of the model, but we also want to explain at which intermediate layer things started getting wrong, right? So we can look at things at the intermediate layer, and maybe we can find out, okay, in this layer of the model, things started getting wrong, and maybe we need to optimize that part of the model. We're also looking into more difficult problems beyond classification, such as regression type of problems like graph alignment, etc. So this concludes the explainability part. I don't think I have time for the other aspect where we are applying machine learning techniques to solve querying part, but maybe I can take 5 minutes to conclude, right? Okay. So yeah, just to give you a high level overview of what the problem that we are solving on the other direction, which is to apply different machine learning techniques to solve query answering over knowledge graphs. So here we have a knowledge graph from the DBpedia, which is a real knowledge graph about different cars, their manufacturers, companies, etc. And over this knowledge graph, we are interested in the following query that find all cars produced in Germany. Okay. So one way to answer this query is to create a query graph like a car node, then a country node called Germany, and then a product age. And we want to find the match of the query graph in the data graph. And then if you try to consider exact matches, then you find only one correct answer, which is I believe BMW 320, because BMW 320 is directly connected to country Germany based on the assembly age. But there are also other cars that are present in the knowledge graph, such as Audi TT or Porsche 911. They are also German cars, but they are connected to the country Germany based on a longer path, such as Audi TT is first connected to company Volkswagen based on the assembly age, and then Volkswagen is connected to country Germany based on the country age. Now, the semantic meaning of this path, country assembly, is same as the query age assembly, right? But it's very difficult for typical database queries such as SQL or SPARQL to get this kind of semantic similarity. And that's what we are doing here, right? We are applying different machine learning techniques to capture this semantic similarity. And our machine learning techniques can tell us that the semantic meaning of the path country assembly is same as the query age assembly. So even though you don't get these relevant answers like Audi TT and Porsche 911 based on SQL or SPARQL, but when we apply machine learning techniques to generate embeddings and then do a semantic search on that space, we can get this kind of relevant answer. So that's the kind of things we are doing there. We have a bunch of works right in this space. I'll be very happy to talk about it later on. Okay, so let me go to the last part, which is I will conclude about our research. Okay, so this is the big picture of our research. We are working in the space of big data, big graphs, and there are many sources. They can come from social networks, RDFs, biological networks, knowledge graphs, etc. And the two other aspects of this research is this is very much interdisciplinary. We do need different kind of skills from machine learning, databases, distributed systems, graph algorithms. But the other important aspect of this research, which also keeps me very interested and motivated in this domain, is they are very much application oriented, right? So in our research, we have demonstrated applications in web search, business analytics, healthcare, cybersecurity, etc. Now, the main takeaway of the overall talk is we looked into the data pipeline of graphs in the context of machine learning. It goes through a number of phases, and what we are looking into is how data management and machine learning can tightly integrate and can help each other at each stage of this pipeline. In particular, in the context of explainability, I have discussed how graph data management techniques such as graph views, fairness, robustness, parallelization, etc., can make the explanations much more user-friendly. And on the other direction, which is graph machine learning for graph data management, I didn't have a lot of time. But here we are looking into how different machine learning, such as embedding techniques, can provide you more relevant answers, which are very difficult to be answered based on more strict SQL or SPARQL type of queries. Okay, this is the last slide, and this is about the future direction. We have also started looking into large language models, and in particular, the synergy between large language models and knowledge graphs. So, large language models often they're very good in terms of conversational type of queries, but if you have more complex queries which requires reasoning, such as complex fact checking, code explanation, schema matching, then they often do not work well. And there, what we are looking into is a graph RAG kind of approach. So you might get more relevant domain-specific knowledge, up-to-date knowledge from a knowledge base or a knowledge graph. So how to retrieve the relevant knowledge given a specific query, how to integrate it with the LLM to generate better results, So that's what we are looking into for some of the downstream tasks such as fact checking, schema matching, etc. And this also shows the synergy of graph data management and graph machine learning. Okay, so I will end here and thank you once again.